I'm honored today to introduce Cassandra Pattanayak, here to speak to us about determining causality through statistics. Casey earned her PhD in statistics from Harvard University in 2011 and has been the Jack and Sandra Polk-Guthman Director of the Quantitative Analysis Institute here at Wellesley since 2013. The Quantitative Analysis Institute is designed to expand the role of statistics in research, teaching, and learning here at the college. I became involved with the Quantitative Analysis Institute after I took a seminar with Casey during both of our first semesters here at Wellesley. Since then, I have worked at the Quantitative Analysis Institute as a Guthman intern in statistical consulting. From its inception in 2013, the Institute, headed by Casey, has provided statistical consulting to faculty and student researchers across dozens of fields of study, ranging from women's and gender studies to astrophysics to economics. Casey has also designed and taught various courses on advanced statistics and causal inference, the subject of her talk today. Now, I have the great pleasure of introducing Casey, speaking this morning on statistics and the search for causality. Please help me welcome Professor Cassandra Pattanayak.
Thank you so much to Julia. And Julia was one of those students who sat in my classroom my very first day actually teaching at Wellesley. So I thank you so much to her for being such a fantastic student. So here's where I want to start. I want to think about this word because. So we're going to do a couple things here. I'm going to talk about the topic of the talk, about statistics and causality, and I'm also going to tell you a little bit about the Quantitative Analysis Institute. But I want to get started with really thinking about statistics and showing you kind of what we do in class. So let's start with this question. Why are you here? You are attending this lecture because. Let's get some responses to that. Why are you here? It's 10 o'clock.
Interesting on the schedule.
Oh, it's interesting the schedule. Thank you. Fantastic. Good. Why else? Who else? Yeah?
I knew that I was being a sucker for it because I just saw the thing that said family therapy in French, and those words just grabbed me.
Yeah.
And then because I am a psychotherapist, I saw then what causes causality, so that it does intrigue me.
Fantastic. So those words I chose for the title. Good. What else? Let's get one more. Yep.
Now it's a big data is it's very hot, so I think you may talk about something related to big data analysis to find something interesting.
Sure. Okay, good. So here's how I want to think about these words. The word because is an English word, and we all know how to use it. But what does it mean when we start to think about actually learning something from data? The framework that I use and that I think we all should be using when we think about learning about causation is what would have happened had we been in a different situation. So what you said was that you're here because my talk was the most interesting in the schedule, right? What you're implying is, I think, if there had been a different talk in the schedule that was way more interesting than mine, you wouldn't be here, right? That's what that implies. You're saying you're here because I included in my title words like French and therapy, family therapy, right? Had I chosen a different title, perhaps you wouldn't be sitting here, right? You're saying you're here because statistics and big data is a hot field right now, right? That's an interesting one. So that's something that wasn't in my control, right? So suppose that big data was not a big thing right now. There was something else that was a kind of the hottest career right now. Then perhaps you wouldn't be sitting here, right? That's how we think about causality. What would the world have been like had we been in a different scenario? And so the questions that are underlying my talk today, that are motivating my talk today, use the word because in several ways. The first example is about voter engagement. She voted because we knocked on her door, we, the canvassing organization. Had we not knocked on her door, perhaps she would not have voted. That's the framework we're using. He recovered from his illness because he received family therapy. Had he not received family therapy, perhaps he would not have recovered. That's the implication with that sentence. Racine's play is more famous than Corneille's because Berenice has more dialogue. Had the character Berenice had less dialogue, perhaps Corneille's play instead of Racine's would have been more famous. That's the way we're thinking about because in this context. I'm a statistician. I work on lots of different projects. The projects that I'm using as examples today are not done. So I'm not going to answer the questions. I'm not going to tell you whether this particular type of voting practice helps, whether this voter engagement practice helps get out the vote, because we don't know yet. It's still happening. I might slip, but I'm not necessarily going to tell you what I know about family therapy versus individual therapy because we're not done analyzing the data and it's not published yet. And we do not know the answer to this question yet. But instead what I'm going to do is show you what I think about when a researcher in an applied field like political science or medicine or French comes to me with a question. What do I think about? How do I frame that question in order to allow them to make a statement about causality as opposed to correlation? So the example we'll talk about first is this voter engagement. So Professor Hari Han from the political science department came to me and told me that she had been invited to evaluate a particular voter engagement strategy called integrated voter engagement, IVE, that's currently being used in Ohio. This started last year, but it's ongoing this year, and we're particularly interested in what's going to happen next year with the presidential election. My student Anne is working on this project, and the underlying causal question is, does integrated voter engagement increase civic engagement, things like voting, things like attending events to help bring out the vote, or events to help pass certain kinds of laws? Does it increase civic engagement among low propensity voters in Ohio, among the type of people who might normally not be as civically engaged? That's the underlying research question. So again, I don't know the answer to that question yet, but let's think about how we might answer it. So we're going to start by thinking about some definitions. We're going to think about the term a unit. And if you think about a data set, perhaps some of you have seen data sets, perhaps some of you have not, but it's got usually a lot of rows in it, right? Like maybe on every row we've got a person. On every row we've got a household. So the unit of analysis is the thing that's on the rows in a data set. So in this case, say the unit is you at a particular time. You are a person who lives in Ohio. Okay? What we're interested in this particular case is the number of civic events that you're going to attend in the next year. Okay? Following the treatment decision, following either someone knocking at your door or not. The causal inference framework that we're using here sets us up such that for each unit, if there are two treatments we're interested in comparing, there are two possible paths forward. And what we're interested in comparing is what would happen to you under this path versus what would happen to you under that path. And that comparison is the really crucial part of this. There has to be something to compare it to. Two possible paths forward. How many civic events would I attend if a canvasser knocks on my door? How many civic events would I have attended had the canvasser not knocked on my door? And if I want to be this organization and make a statement like, our program brings out the vote, it's not enough to say we know what happens when we knock on the door. We need to also be able to say something about what would have happened had we not knocked on that individual's door. And that's the fundamental idea here of causal inference. So we're going to start to set this up in a table. I'm going to have a few tables here. My advisor always called these the science table. The idea is that this shows the truth that we wish we knew, although we don't. Okay? So we've got one row for the one unit. This is you. This is you, the voter in Ohio. And here's how we're going to think about this. We're going to think about this as potential outcomes. What would your outcome be? How many civic events would you attend if we knock on your door? And what would your outcome be? How many civic events would you attend if we did not knock on your door? And the idea here is that those are two numbers that are just fixed. Even before we start the study, we can say there is something that will happen to you under this condition, and there is something that will happen to you under this condition. Right? Even before we gather the data. We're trying to separate our goal from the actual information we're going to collect to learn about that goal. So we'll call those potential outcomes because potentially either one of them could be the data that we collect. And so in this little example I've made up here, we might say that you, the voter, would attend 3 civic events in the next year if you have your door knocked on, if you're part of integrated voter engagement. And if you are not part of integrated voter engagement, you would have attended 1 civic event. So the idea here, the definition of a causal effect, is the comparison between these two, right? The comparison between these two. How many more civic events do you participate in than you would have had you not been in the integrated voter engagement program? This is the definition of a causal effect, a comparison between the potential outcomes. And I can define that before we even start collecting data. I know that this is my goal, to learn about, for you, what the difference is between what would happen under one condition and what would happen under another. There are certain scenarios where we can see both of these potential outcomes, specifically fiction, right? Fiction. Okay, who's seen It's a Wonderful Life, the movie? Okay, so I haven't, but I use this as a teaching example all the time. All right, so here's the general idea. I'm Jewish, so we don't watch this as a kid. Okay, so It's a Wonderful Life. Here's the idea. The potential outcome under control, so I'm just using a 0 here, but to denote control, is the actual world that we already saw. So the idea here is we have George Bailey, right? He's looking back in his life, and his actual life has happened. Here's what the world is like, given that we have George Bailey alive. But what he's saying is perhaps the world would have been better had I never been born, right? For those who've seen the movie, is that right? Right? Perhaps the world would have been better had I never been born. In real life, we don't know what the world would have been like had we never been born. But because this is fiction, we get to find out. We get to observe this counterfactual world as if George Bailey had never been born. And the causal effect of George Bailey's birth is the comparison between the world if he'd never been born and the world in which he was actually born. Okay. But only in fiction do we get to see that comparison. So here's the fundamental problem of causal inference. Right? All my assignments and my exams have a question on it. What is the fundamental problem of causal inference? To make sure this part sinks in, for each unit, for each person in our study, each household, each rat, whatever it is that we're studying, each French play, we can observe in our data no more than one potential outcome. We either get to see what happens to you when we knock on your door, or we get to see what happens to you when we don't knock on your door. But we don't get to see both. For no unit in our study, for no person in the study, do we ever observe the causal effects. Do we ever get to actually see the comparison between those two? Instead, causal inference, learning about causation, is fundamentally a missing data problem. For every person in the study, we're missing information either on what would happen to them under this treatment or what would happen to them under this other treatment. And our job as statisticians is to try to fill in, based on our best guesses, those missing potential outcomes. So anytime you read a sentence about causation from a study, what that researcher at least should have been trying to do is make guesses about things that we're missing. And that's more generally true in statistics. Statistics is about making guesses about things we don't know based on what we do know. But specifically for causal inference, the way you want to think about any article, any paper you read about in the media, for example, did the researchers have the information they needed to guess what would have happened to each person had they been in the other condition? And if not, probably it's not really causal. Okay. So how do we learn about the missing potential outcomes and therefore the causal effects? In the little science table that I showed you so far, there was just one row, right? One unit. But the way that we gather information about what would happen to people, happen to units under one condition versus under another, is replication. In other words, we have more than one person in our study. Right? We have more than one person in our study. So we have some people whose doors are knocked on. We have some people whose doors are not knocked on. We see what happens to each of them. And under the really strong assumption that those two groups of people are comparable, perhaps we can use them to guess about what would have happened under the other condition to each person. If those groups are not comparable, we've perhaps got a problem. Okay? My own research focuses on what to do when those groups are at least initially not comparable. Okay? So let's think about one of the tricky assumptions that I always end up teaching about in this context. The table I showed you so far had one row, and it said U. And we said there are two possible treatments, either IVE or not. So there are two potential outcomes for you, right? Now I'm going to tell you that there are two people in the study, right? You and me, okay? How many columns do I need? Are there still two potential outcomes for me, or are there more than that? I'm going to argue there could be more than that. Anybody have a sense why? How come when I add rows to the table, I might also have to add columns? How come there might be more than two paths forward for me once you're in the study? Yes?
Could be other defining factors.
Good, like what?
I don't know, like nationality, culture, what side of town you live on, how many other people in your family, other confounding factors.
Yep, sure.
Make it or not.
Good. Okay, good. So let me comment on that really quick, and I see another hand in the back. So one idea here is that there's a lot of characteristics of each unit, each person that aren't in this table, right? The framework that we're going to use here is that those things are fixed at the time when we assign you treatment or not. So if I wanted to expand this table, one thing I would do is add a bunch of columns, exactly as you said, corresponding to those things. If those things are fixed at the time of assignment to treatment, then I don't have to talk about multiple outcomes for them, right? My gender is my gender at the time of treatment, and it's not going to change based on whether you knock on my door. Okay, that's right. That's a reason to add columns to the table. Why else? Go ahead.
I could interact with you, and you could spread your IVE to me.
Yes. Okay, so that's exactly right. So here's the idea. There's this assumption. This is part of the assumption I'm giving you here, the stable unit treatment value assumption. This was invented/named by my advisor, who is an awesome, really, really smart man who invented lots of fields of statistics, but was not great at naming things. Okay, so SITVA. There's lots of really awkward terms in here. SITVA. There is no interference among units. In other words, my potential outcomes, what would happen to me if you knock on my door and what would happen to me if you don't change depending on whether your door gets knocked on. What would happen to me under either treatment is not affected by your participation in this study. That's often a really tricky assumption. So let's talk through why. But it sounds like some of us already have intuition for why. So the notation I'm going to use here is y, in other words, number of civic events, parentheses, what would happen, what treatment you get, what treatment I get. Okay? If both of us have our doors knocked on, perhaps what will happen is that I go to 3 civic events and you go to 2. Perhaps that's the case. I'm not saying this is data we actually collect. Rather, we're having this discussion at the level of what we wish we could know. right? What we wish we could learn about. Okay, what if I have my door knocked on, but you don't? Well, perhaps I still would have gone to 2 civic events, but since your door was not knocked on, you only would attend 1. Perhaps that's the case. Okay, and I made this up, but I made it up this way for a reason. Perhaps neither of us has our door knocked on. Well, what we said is that you attend 1 event when your door is not knocked on, and perhaps I attend 0. Okay, so far, no interaction, but here's where I'm going to put in an interaction. Suppose that your door is knocked on and mine is not. You go to 3 events. Had your door not been knocked on, I wouldn't have gone to any, but you're my neighbor and you invited me along, right? And now I go to 1. This is the interaction problem. And the issue here is that if there's interaction between units, then we have to add a lot of columns to this table. And each unit is going to be assigned to just 1 treatment, so only one of these columns is actually going to be observed, right? And if I have 4 columns here and only one of them observed, there's a lot of missing data here, right? In other words, if you have a situation where you believe there could be interaction, there's a lot of missing data. There's a lot of missing data, and the problem becomes much harder. In fact, we don't really know how to deal with that problem most of the time. That's why we have this assumption, which we've fancily named SUTFA. Okay? So in many contexts, we work really, really hard to define the problem such that we don't have this kind of interaction issue. The argument I'm making here is not about data analysis exactly, but rather that I don't even know how to define the quantity I'm trying to guess at if we have this kind of interaction. Because if everybody is knocking on their neighbor's doors, inviting them to the events they're planning to go to, we've got to add a lot more columns, right? Everybody has a lot more possible paths forward. We only see 1. We've got a ton of question marks. What is the definition of causal effect in that context? I don't know anymore. What we typically do when there's this kind of problem is define the units differently. So for example, in the education context, if we're worried about kids affecting each other, perhaps the row in the data set is the classroom or the school, right? And classrooms are less likely to affect each other than individual students, perhaps. So usually we assume away this problem, but I wanted to mention it because I think it helps illustrate the importance of this notation and really refining what our goal is. In my view, we'd better know what our goal is before we try to gather data to learn about our goal, to accomplish our goal. And often in data analysis, that's something that's missed, that we just run a regression. That's a term probably a lot of us have heard. Why are we running the regression? To answer the question. Why would the regression answer the question? I don't know. First, let's define what it is that we're trying to guess at. What information do we wish we had? So I'm going to make the table a little bit bigger. Suppose we had 4 units. I'm now going to include columns for what I'm calling covariates, backward information, exactly as you said. So suppose we have 2 males and 2 females, right? Here are the potential outcomes, and all you need to know here is that this is the notation I'm using to represent what would happen to this person if they get IVE. This notation is representing what would happen to this person if they don't. That's the idea. So for each person, there are 2 potential outcomes. For each person, there's a unit level causal effect. For this person, whatever number is here, the difference in these 2 things is the effect of knocking on that person's door. But what do we actually observe in our study? Well, suppose that we knocked on this person's door and this person's door, but we didn't knock on persons 2 and 4's doors, okay? So we observe some of the potential outcomes, but we've got a bunch of question marks, including everywhere in the causal effect column. We don't know anyone's causal effect, and this is typical, right? This is what the data set actually looks like. And this is one of the crucial places where this framework helps us think about causation, because when you get a data set, there's just 1 column for how many civic events. But what we need to think about is that really represents 2 columns, how many civic events you would have attended had we knocked on your door, and how many civic events you would have attended had we not knocked on your door, and we're missing half the data in each of those. Our job is to fill it in. I'm going to stick in some numbers here just so we can be more concrete. Suppose these are the numbers that we observe in our data. In this particular study, we're randomizing whether we knock on your door or not. So I randomized. It was fun. I literally pressed the button to decide whose door was going to get knocked on. And so now that we have this data, we can try to make guesses. And the general idea is that if we have this male, who was randomized not to have his door knocked on, our best guess at how many civic events he would have attended had his door been knocked on perhaps can be guessed based on this other method, right? If we think that's the only thing that mattered, or if we randomized which one is which, then on average, the 2 groups should be similar. If we randomly assign some people to have their doors knocked on and some people not to, then to the best of our knowledge, right, there's no reason that the people whose doors are knocked on should be different than those who are not, and perhaps we can use them to fill in each other's missing potential outcomes. That's why randomized experiments are so great. That's why they work. Because on average, the units who have potential outcomes observed under 1 treatment are in general similar to the units whose potential outcomes are observed under the other treatment, and we can use them to guess at each other. which is what this shows here. Right, so I'm filling in for each unit potential outcomes based on somebody who was similar on the background characteristics but got the other treatment, and now I can guess at the causal effects for each of these people. If I'm interested in an average causal effect, which is common, then I take the average of this column. That's it. Okay. That's how randomized experiments work. Okay. All right, so voter engagement, we don't know the answer yet. We don't know the answer yet because this particular voter engagement program, the impact is thought to happen over time. That's the point. We're going to knock on your door lots and lots of times. So over the first year, we saw whether or not there was a difference in 1 year of this integrated voter engagement problem, but the real results are going to be interesting after 3 years of really engaging in with these voters. Okay, so here's another study that I'm working on. This is a study that I'm involved in because I happened to run into Sue Marcus at a conference. So Sue Marcus is a Wellesley alum, which I didn't even know, but she is also a biostatistician, recently retired from Columbia. And she said, hey, if you have any great students, I've got some really interesting problems to work on. So my student Diana Schron got involved in that. She is now at Columbia Dental School, actually. And this particular study has to do with which kinds of therapy might prevent anorexia in adolescents who are already showing some signs of anorexia. So medical health diagnoses such as anorexia are based on a certain number of criteria. And there are 4 criteria that you have to have checked off to have anorexia. So people, I keep on saying students, adolescents in this study have 1 or 2 or 3 of those checked off, but not all 4. That's the idea. And so the question is, does the usual therapy, which is individual based, as you and the therapist sitting there, work as well as, better than, less well than having the whole family come and talk to a therapist? That's the question. That's the question. And what was interesting about this study is that they tried to do a randomized experiment, because that would be great, right? And people were hearing about this family therapy idea. And these families, really, really need help. And they said, I would love to have a shot at getting that family therapy. Let me enroll in this trial. And then when they got assigned to individual therapy, they said, never mind. I don't actually want to do this. Okay, that was the problem. And that sometimes happens in studies. People want to be included in the study because they want a chance to get this new kind of treatment, but once they get assigned to the other one, wait a second, I don't want to do this. Okay. And that was a problem for the study, right? That's a really big problem. And what the particular collaborators here did about it is they called Sue Marcus, which is a good idea. The psychiatrist called up Sue, and she said, let's let those people choose. So we're not going to tell people when they enter the study that they can choose which treatment they want, but if they get randomized and try to quit, let's at least follow them. Let's say, okay, you can have the family therapy, and then follow them. With the idea that at the end of the study, some of the people will have been randomized, which will help, and otherwise it's just a non-randomized study, and at least we'll have some data. Okay? And that's called a doubly randomized or doubly treated preference trial, which is Sue's area of research, which has been really interesting to study. What I'm going to use it for now is just an example to think about what we do when we can't randomize. Yes?
Why did you have to tell them to begin with? Is that a legal requirement? Or
Tell them
that there were certain people being tested on a family basis and certain people being tested on
because they have to consent to the trial. They have to consent to being randomized, and they certainly can't blind it because either the parents come or they don't to the therapy. Yeah, so it's not like a pill where you can.
kind of legal.
Yeah, you can't.
It's more ethical than legal.
Oh, okay.
Yeah, you have to have people know what the possible options are. Even in a medical study where you can blind people to which pill they're actually receiving, they have to know what the options would have been. Yeah, you can't fool them. Okay. So I'm going to use this example as a chance to talk about what can happen in a non-randomized study. What can happen in a non-randomized study? And the reason that this is so important, first of all, is lots of times we can't randomize or people don't want to be randomized. But also, there's a lot of talk these days about big data, about personalized medicine, right? Why can't we take advantage of electronic medical records and look at all the data that's out there and see whether people tend to do better under this thing versus this other thing, right? Just based on who's getting what kind of treatment from their doctor. This is the reason. Okay, I'm not a huge fan of that kind of technique. So I'm going to try to convince you of that. So here's a science table. Here's an example of what the truth might be, not our data set, but what the truth underlying our data set might have been for 4 people participating in this study. So the idea is we're interested in percent of ideal body weight at the end of the study, right? There's a goal. So the goal is at least 100, right? For these patients, it's often less than that, okay? So for each of these patients, by the end of the study, here's what their ideal percentage body weight would have been if they received the family therapy. And for each of these 4 people, here's what it would have been under the individual therapy. Now, I'm not saying that I actually know both these numbers for any person in our study. I only know one or the other. But for the purpose of figuring out what we wish we knew, we want to write them both down or get an idea of them. So the idea is for each person, there's a difference between these. This person would have 100 as their value under family therapy and 95 under individual therapy, and the difference is 5. Right? So for these two people, the family is better, but for these two people, the individual therapy seems to be better. And often what we're interested in is an average effect so that we can just recommend to anybody who comes in the door, on average, a certain treatment is better. And in this case, on average, the numbers are negative. On average, it seems like individual therapy is better for this little fake data right here, okay, with these 4 people. Okay? But what happens in the course of a medical study when real medical data is collected? Doctors don't flip coins to determine which treatment they give to someone. Instead, they think about which treatment they guess would probably be better for that patient. And that's what patients do and families do when they have decisions to make about their care as well. Let me try to guess which treatment is going to be better for me, and I'll take that one. Okay? So let's assume, for the sake of argument, that everybody's really good at that guessing. Okay? I think I know which treatment is going to be better for me, and that's the one I'm going to get. So again, the average of these numbers right here is negative 2.5. The average effect is negative. Okay? What happens if each patient chooses the treatment that's better for him or her? Well, this first person, right, would be better off under family, so we're going to see this number. The second person, better off under family. Third and fourth people, better off under individual. Those are the numbers we're going to see. Okay? Now, if this is the data we collect, what do most people do with this data? What most people do with this data is they say, okay, let me report the average outcome for people who had family therapy and the average outcome for people who had individual therapy, right? And if we do that in this case, we're going to get the wrong answer because we're not taking into account the fact that each person tried to choose the treatment that was going to be better for them. And that's what all those electronic medical records are. They're the result of what a doctor hoped was the best possible scenario for a particular person. So we've got to be really, really careful. You can't just look at the average outcome for these people, the average outcome for these people, because you're going to get the wrong answer. The observed average causal effect here is 12.5, the average of these two numbers minus the average of these two numbers. Implicitly, if we, again, state that family therapy is better because the average of these two is better than these two, what we are implicitly imputing, guessing for the missing potential outcomes, is that the average of these two numbers is a reasonable guess at what would have happened to these two people had they had family therapy, and that the average of these two numbers is a reasonable guess at what would have happened to these people under individual therapy. That could have been a reasonable guess if these 4 people were randomized to get family or individual, because then I might expect that these 2 people are similar to these 2. But instead, they were not randomized. Each person chose the treatment they thought was better for them, and these, in fact, are terrible guesses. What would be a better guess? Well, if I know that each person was trying to maximize their own treatment, my best guess at this person's outcome under family therapy is that it's anything less than what they actually got under individual therapy. So 97.5, really bad guess. Right, really bad guess. Causal inference is about guessing, just like all of statistics. Okay. More generally, how do we actually approach this problem? We try to make use of background variables to separate people. So if I knew that at baseline these 2 people were moderately sick and these 2 people were severely sick, then looking at my data set, I would know that I can't answer my question because the people who are moderately sick all got family therapy, and I have no good information with which to guess what would have happened to them under individual. And the people who are severely sick, in my little example, both got individual therapy, and I have no information with which to guess what would have happened to them under family. That's the idea. Okay. So you better get really, really good baseline variables, and often the baseline variables that actually predict which treatment people get in the medical context are not recorded in those electronic medical records. That's the issue. Okay, so it's really, really hard to do what we're all trying to do, which is take advantage of the information that's out there to the best of our ability. This last one's quick. It's very ongoing, but it's exciting to me that I've started to get involved in some of these humanities examples. I think this has been really fun. So Hélène Belly is a professor in the French department here, and she studies French plays written in the 17th century. And I have a student working on this project right now named Joanna Milton, who happens to be a biology major, so it's fun for her to get into the French plays. What Hélène is interested in is 2 French playwrights, Racine and Corneille, who were writing plays and having their plays performed in Paris at the same time. And the way historically this happened to work out is that whenever Racine wrote a play on a certain topic and it was performed in his theater, Corneille said, wait a second, let me really quick write a play on the same thing and it'll be performed in my theater, right? And often they were going on at the same time. And what typically happened is that one of those plays won in the sense that it became famous and part of the literary canon. The other one we all kind of forgot about, right? And in fact, for my purposes today, because I don't have the whole data set yet, I was using Wikipedia to try to figure out which is better. It's really clear from Wikipedia which play won. Okay, it's really, really clear. And then, Cornet would write a play on a certain topic, and Racine would really quickly write a play on a similar topic, and one of them would win. Okay. So the question that Alain is asking is, can we use quantitative measures of the words and phrases and verses in these plays to determine which one was going to become canonical and which one we were going to forget? Okay? That's what we're doing. So I'll show you an example of the kind of analysis that we've been working on. Again, this is a very new project. So what we did is we took the play, and each of the plays, and we turned them into data sets where a certain person, a certain character spoke for a certain amount of time. So we recorded that as one row. This person spoke for this long. Next row, this person spoke for this long. And what we did for this particular set of plays, both about a character Berenice, is we looked at how many literally lines, verses, were spoken consecutively by Berenice in Corneille's play versus in Racine's play. Okay? And the kind of thing that we're observing is that in Racine's play, which turns out to be the one that's more famous, there's a lot more instances of Berenice speaking very quickly. In other words, more dialogue, right? As opposed to longer speeches by Berenice. Okay, so that's going to be really interesting. I think there's a lot of interesting things we can get at. But can we learn anything causal? Okay, and I want to be really hesitant about that in this case. Is Alain going to be able to publish a paper that says Racine won because Berenice spoke more dialogue, right? Probably not. I also don't think she needs to use the word because. I think this kind of analysis is innovative and correlation is going to be interesting enough. But if you think about turning this into that kind of causal framework and putting rows into that science table, what is that missing potential outcome? What would Racine's play about Berenice have been like had Berenice spoken less dialogue, right? And everything else stays the same. We can't impute that number, right? We're not going to be able to get good enough information to guess at what would have happened to each play under another condition. We're just not. Okay, it's not going to be possible. But in my view, that kind of framework is crucial for realizing that we're not going to be able to do that, right? And that doesn't mean it's not an interesting question, but often what thinking carefully about causal inference does is it tells us when we're going to stop. And what I say to my students is not every data set answers every question, and that's okay, right? That's okay. All right. So what I want to do just for a couple minutes here before we wrap up is tell you about the Quantitative Analysis Institute at Wellesley. We've got a nice website you can check out, and Julia already mentioned it briefly. I was hired by Wellesley 2 years ago, so I came June 2013. And I'm Wellesley's first statistician. So my goal is just to make statistics at Wellesley in any way that we can, and that's what I've been trying to do for the past couple of years. What I said when I first started this job is, I'm the director of the QAI, and that sounds really fancy, but it's just me, right? It's just me. I am the QAI, and my office is the QAI. However, I don't really get to say that anymore because now I've got this nice big stable of students. It's a lot of us now working with statistics at Wellesley, which is really exciting after just 2 years. So very briefly, I'm going to tell you about the different components of the QAI, what I've been doing in terms of teaching and pedagogy, what we do in terms of statistical consulting, and what we do with our students. Okay. So one thing I'm really excited about in terms of pedagogy, since I am only one person, I am the only statistician at Wellesley, I can only do so much teaching, right? I can only do so much. And so we are partnering very closely with Wellesley's Blended Learning Initiative. Now I think you'll hear that every Wellesley professor is every professor everywhere is a little bit skeptical of the whole online learning MOOC thing. I believe there's a lot of value to sitting in a classroom and looking you in the eye to see who's nodding and who's not nodding, and that's what I'm doing, and about half of you understood what I said, so that's great, okay? But these online resources allow us to have a much bigger audience, right? And so I've had a lot of my lectures recorded. It's really fun. I was super pregnant while I did it, so you can go back and look. It's public, okay? You can go to the QAI website and sign up to have access to this. You can see me recording lectures for different courses. My students are also making recordings, how to do this certain thing in certain software. Joanna Milton, who's been working on the text analysis, is building some videos that Wellesley students can watch about how to do text analysis. Using statistical software. How do I use different kinds of statistical software even just as a beginner? Those kinds of videos are now available online, which I'm really excited about. The online materials we're creating are aimed at Wellesley students. I use them as part of my class. They're created by Wellesley students a lot of the time, although many of them are created by me, but they're also available to the public, which I think is really exciting and a contribution to the profession and the statistics teaching world as well. On campus right now, I'm teaching a couple of courses. I teach applied data analysis, which is called QR260. That's a second level statistics class. It's an intermediate statistics class. It has as its prerequisite anything that meets what's called the QR overlay. And I'll talk about QR in just a moment. So any first level data analysis class is a prereq for my class, which is really exciting to me because it means I get students from a big variety of fields and it leads to some nice discussions. That's a course I've also taught over the summer, not for credit for the past couple years. Going forward in the summer, I think we're going to start using the online resources more to get more students involved in that summer program. Last winter session, we did a pilot using these same online materials for students who didn't even have to be on campus. So I had a student who was in Pakistan at home watching these videos and participating in the course, which was really a nice thing to be able to do. I also teach an upper level course on causal inference in the spring, which has as its prereq QR260 or a few other second level data analysis courses, such as in the economics department or the sociology department. And we also offer different kinds of workshops and events. So for example, we brought in a speaker, is the dean of the graduate school at Harvard, also a statistician, and we did a chocolate tasting and analyzed that data, which I thought was fun. Just to mention QR quickly, because this is a question I get a lot. A lot of parents are aware of the quantitative reasoning requirement at Wellesley, and how does my position differ from that? I work closely with Corey Taylor, who's the director of the QR program, but they are distinct. What the QR program does is it administers a test to every incoming student to make sure they have a certain level of quantitative abilities, and depending on that test, they either take a certain course or not, right, when they come in. And then, in addition to that, the QR overlay requirement requires every student to take at least one course from a list of courses that have some statistical content. Okay? That's a great program. We have that. My role is to create a program for students who are interested in pursuing statistics and want to go above that. Okay, so my courses have as the prereq one of those QR overlay courses. That's the distinction between what we do. But you'll see that my courses have this QR in them as part of the title because I don't have a department. And Corey has been very generous and shared her department with me. Another thing I've done on campus is start a statistical consulting service, and this has been really, really fun. This means that as I sit in my office, my 9 a.m. appointment might be about rats, and my 10 a.m. appointment is about galaxies, literally that's happened, and my 11 o'clock appointment is about children at the Wellesley Child Study Center, right? My job is to listen to whatever researchers are working on and see if I can contribute something useful. Right? This is unusual to have this sort of service, especially involving undergraduate statisticians in a liberal arts college. And it's not all that common at the university level as well. So we're really lucky to have this service, in my opinion, and I'm really lucky to have this job because it's really fun. Okay. The other thing I do, to the best of my ability, is create opportunities for students. Right? So I teach courses and I make materials available, but I also consider what I'm doing an apprenticeship program in a lot of ways. There are a lot of job opportunities right now for students with data analysis and quantitative skills. And so part of what I'm trying to do is give students the backgrounds to be able to jump right into those jobs. So Julia mentioned that she has worked as one of the Guthman Fellows in Statistical Consulting. These are students who work closely with me on the Statistical Consulting Service. So these are students who will come with me to a meeting where we hear about a researcher's data analysis issues or study design issues, and we help to the best of our ability, and often it's the student who will follow up and provide advice as that project moves forward. And my hope is that in addition to making my job possible, those students are learning something about how to be a statistician as well. I also have research assistants for projects that I'm working on and for faculty across the college. I increasingly hear from people across the college saying, hey, I could really use a student with data analysis skills. Can you recommend someone? So that's a lot of what I do. And if you look at our website, you'll see how I'm doing that. Part of what I'm doing is kind of being a clearinghouse for students with a certain set of skills. And faculty at Wellesley know that a student who's taken, say, QR260 will be able to help them in some very concrete ways. All my students are also teaching assistants, both for my actual courses online on campus and online, right? So for winter session, I employed a student to help me with that. We have course development assistants, students working on creating these online materials or helping me create new courses, and more. There's a lot of different opportunities for students here. All right, so I'll stop there. I'm happy to take any questions, but thank you for choosing my lecture based on its description. Thanks so much. Yes?
How do you stop all the rest of the world making the simple mistake of not understanding what you were talking about?
So there's a lot of us out there, there's a lot of statisticians out there working hard on this. You know, I could talk about this for an hour. In my opinion, different people working on things like medical data are trained to varying levels of success, right? What I do about it is teach and publish, right, and do my best to be involved in these kinds of projects. I'd say rather than how to stop them, I'd say how do we support them? How do we support you know, things being done right? And the best way is to be involved in it and to train really great people to go forward and work on it. Yeah, and there are really good statisticians involved in these projects. But I also think that, especially in personalized medicine, there's a lot of things slipping through the cracks. That's my opinion. And you know that, because every other day the newspaper tells you to drink coffee or not, right? So you know that's happening. Yeah, there's another hand over here somewhere. Yes? No? Other questions? Thank you so much.